Professors FM.
Hi, Why This Universe listeners. Welcome back. And what you're about to hear is something different. This is an episode of our Ask Us Anything segment that we have usually just hosted on our Patreon. So we're changing things up a bit. Now our Ask Us Anything streams will be public. We'll be posting them from now on our usual podcast streams. So wherever you're listening to this now, you'll get future months as well. But you can also access our backlog of over 30 more of these Ask Us Anything episodes from over the past year or two, and you can do that on our Patreon. You don't have to pay for anything. It's open to free members. You just go to our Patreon, which is patreon.com/whythisuniverse, or you can just click the link in this podcast description, and you can, if you're bored one day, listen to our whole backlog. However, if you would like to ask us a question for a future segment, you can only do that by being a paid Patreon subscriber. So that helps us keep the podcast alive and is a great way to show your support if you like our show and want it to keep existing. So with that all being said, enjoy this segment. Hi, Dan.
Hey, Shalma. It's been a little while.
Yeah, it's been a while. So this is our first Ask Us Anything in a few months. I guess we took a little bit of a break. Dan and I both started kind of new jobs, I suppose.
Mm-hmm.
Dan's
been busy.
Dan's been busy getting started at University of Wisconsin-Madison.
That's right.
I don't know. Is there anything you want to share?
It is great. Yeah, I like Madison, the city, a lot. The university is wonderful. My colleagues here have been really welcoming, and I'm really excited about the science I'm doing with the Wisconsin Ice Cube Particle Astrophysics Center, and especially all the neutrino astronomy stuff we're doing here. It's great. It's really fun, really exciting.
Yeah, and then I started a fellowship for the spring at Quantum Magazine, so you could find my articles slowly coming out over the course of the next few months. Just to plug that, I guess.
You should.
Okay, great. So we have some questions from the past few months. So the first question comes from Joe P. If photons and neutrinos don't decay and lots of processes continue to produce them, how does our universe not fill up with them?
So first of all, there's energy is conserved. So we can't have more energy in neutrinos or photons than we used to. We can take things that have more energy or more mass and break them into mini neutrinos or mini photons, and to some extent that's going on. But I'll also say the universe is just getting bigger in volume. So, you can keep putting stuff in a box, but as long as that box is growing bigger than you're putting stuff in it, it's never going to fill up. In fact, the most of the photons in our universe and most of the neutrinos are left over from the Big Bang. And, they're about the same total number as, in the relatively early universe. And the universe is way, way, way bigger now. So we're actually a lot less full, per se, than we were back in those early times.
Right, like right after the Big Bang, the universe really was full of photons.
Yeah.
And now it's less full.
So right now we have 411 photons per cubic centimeter in our universe. But, if you go back to a time, like a second after the Big Bang, if I do a little bit quick math, that's about 10 to the 30 times more. So like about 10 to the 32 photons per cubic centimeter at that time.
Sounds
so
like
a lot more.
A lot of photons.
Yeah, a lot of photons.
Right. Yeah. Actually, I kind of want to ask, just because I got a little confused about this, because we said, when the universe is expanding, those photons from the early universe, from the cosmic microwave background, are actually losing energy because they're getting stretched out, right?
Mm-hmm. Yeah, cosmological redshift. Yeah.
Right. So that is like a slight addendum to what you said about energy being conserved, right?
Yeah. Okay. So it's a perennial debate between cosmologists about if cosmological redshift as a phenomena conserves energy. I don't, it depends what you mean exactly, but it is true that individual particles lose energy as they get stretched. Mm-hmm. Whether that goes into the space-time or whatever, I don't know. But definitely the energy of those photons goes down as the universe stretches.
Right. Okay. Interesting. Subtlety. Okay, great. So our next question is from Rad. We missed you, Rad. Is the Ice Cube Observatory you mentioned in a recent episode capable of detecting all 3 neutrino flavors? I.e., can it tell whether it's an electron, muon, or tau neutrino that hit? Do we have estimates for neutrino flavor abundances depending on the source? Also, is there such a thing as a cosmic neutrino background that is a similar remnant of the Big Bang as the CMB? If yes, could we peer further back in time than we can with the CMB by detecting these primordial neutrinos? Great questions.
I think the answers are yes, yes, and yes. So let's dig that apart.
Right.
So the Ice Cube Neutrino Observatory observes neutrinos in a couple of different ways, or a few different ways. So first of all, neutrinos come in 3 flavors: electron neutrinos, muon neutrinos, and tau neutrinos. And they can all interact just by like scattering elastically off a nucleus, and that just makes a big shower of energy. Or they can scatter and transform the neutrino into an electron, a muon, or a tau, a charged particle, depending on the neutrino's flavor. And those lead to different kinds of signals. So if you just create that big old shower I described before, pretty much all 3 of those flavors look alike, so you really can't tell which flavor created it. And if you have electron neutrino scatter inelastically, so making an electron, then you get a shower, but it's a little bit of a different shower. It's what we call an electromagnetic shower, and you can maybe identify that if you really get a good measurement of that event. If it's a muon neutrino and it produces a muon, that muon will travel like straight through the detector in a line, depositing energy as it goes. We call that like energetic line a track, muon track, and those are really distinctive. So we see a bunch of those muon tracks, and those come from muon neutrinos. And then the tau neutrinos produce some kind of more unique events. We don't have very many of these, but we have detected several events that we attribute to tau neutrinos. What goes on here is the neutrino comes in, it scatters, it makes it a tau lepton. But tau leptons are really short-lived, so they don't travel all that far before they decay. So what you get is a picture where the first collision happens, there's kind of a shower, and then the tau travels a little bit farther in the detector, maybe hundreds of meters, and then it decays, making a second shower. And we call that a double bang event.
Not just a bang bang.
we could have called them a bang bang event. Actually, I kind of like the sound of it. But no, we call them double bangs. And there are other versions where you see like part of a track in a shower. We call those lollipop events, or things like this. So not all of the events can we point to the flavor, but if we look at all this statistically, we can measure the flavors of these neutrinos pretty well. Right now, we have measurements of the flavor ratios of the neutrinos we're detecting, and we expect them to come in about equal flavor ratios, pretty close to 1 to 1 to 1. And the data is consistent with that, but, the error bars are still pretty big. In the future, like if we build the Ice Cube Gen 2 Neutrino Observatory, which will be an order of magnitude more sensitive than Ice Cube, we might be able to do that with some of the brightest individual sources, as opposed to just all the neutrinos put together. But so far, I don't think we can say too much about the flavor ratios of individual sources. There just aren't enough of them yet.
Okay, and then the remnants from the background, the remnants from the Big Bang and neutrinos. Yeah. How about that?
There is indeed a cosmic neutrino background. So the cosmic microwave background was a relic from 380,000 years after the Big Bang. That's when photons stopped scattering with other particles like electrons and became kind of free to travel in straight lines. The neutrinos did something analogous to that, but a second after the Big Bang. Okay, so much, much, much earlier. So basically, because they interact a lot less than light does, they were liberated from scattering much earlier. So Rad's intuition is right. If we were able to measure this in detail, it would tell us like analogous things to what the cosmic microwave background tells us, but from a much earlier time, from much earlier after the Big Bang. The problem is it's really hard to detect these neutrinos. They're not only neutrinos, making them hard, but also they're really, really low energy, even colder than the cosmic microwave background. And so far, we just don't have the technology to do that, at least directly. We can tell those neutrinos are there from their overall energy density and their impact on things like large-scale structure and the expansion history of the universe. But we don't detect the individual neutrinos yet. We don't have any way of doing that just yet.
Cool. Okay, so our next question is from Guys Whites. I hope I got that this time after chickening out last time with trying to pronounce your Dutch name. So thank you for the help. Okay, so the question is, could you please explain Bell's theorem and its significance in quantum mechanics?
Oh, wow. Okay.
That's a big one.
Yeah. Okay. So it has to do with quantum entanglement. And it has to do with what we think is deep down going on in quantum physics. So, so in the traditional, original, like the way that the pioneers of quantum physics thought about quantum physics, they pictured a situation where you have some particle or something that's in a quantum state. And that means it has a wave function, and that wave function allows it to kind of be in a lot of different places at one time and have a lot of different speeds at one time, have different energies at one time. It kind of smeared out in all these respects. And then when you make a measurement of that thing's, say, position or velocity or energy or something, you make a measurement and it collapses that wave function down into a particular state that you measure. This is called the Copenhagen interpretation of quantum physics. And frankly, it's like really philosophically difficult to accept for a lot of people, and myself included, because you have to ask, like, why does observing something collapse it? What's special about the act of observation? And to be clear, it's not that it just has to interact to collapse. It really does seem to have to be observed by, something conscious or something, which is very weird.
Well, I wouldn't necessarily go that far, I guess.
I think that's what it really says.
Yeah. Well, I guess my addition to that would just be, we don't know for sure that it's about consciousness at all. It might just be that, like, to do a measurement, you gotta, there's kind of like a lot of macroscopic stuff that has to happen. And maybe something about
so you're pointing to like quantum decoherence.
Yeah, exactly. Maybe something about the translation from like a microscopic quantum system to some macroscopic information or something. Maybe something in that translation, like you said, decoheres or just kind of makes the system not quantum anymore. That's at least where I'm standing philosophically right now.
I definitely agree that people make that argument. I'll say I don't find it compelling. I don't think it really solves the problem. I think it conceals the problem, but it doesn't really solve it. But you know what? There's some people who think it does solve it, and I'm not going to.
I'm surprised.
Make any definitive pronouncements here. So the thing I like, the solution I like to this problem is something like many worlds quantum mechanics or Everettian quantum mechanics, where wave functions don't collapse. Observation doesn't do anything other than, take an observer and like make them experience one part of the wave function at a time. So when you're done making that observation, there are many different universes or branches of the wave function or whatever in which you observe all the quantum possibilities. That doesn't require anything special to go on, except there has to be a quantum multiverse. So, but I'm comfortable with that.
Nothing special.
Yeah. Ordinary quantum multiverse.
I guess the point is that there's different ways to, different ideas about how it is that quantum measurements give you classical results, and we don't know exactly which is right yet, but maybe we will one day.
and back in the day, guys like Einstein and others thought that maybe there would be a third kind of solution to this problem. And that involved what they called hidden variables. So they said, well, the wave function looks non-probabilistic. Like, you don't know how it's going to collapse and all this stuff. But maybe that's just because you don't know everything there is to know about the wave function. Maybe it's, analogous to a classical object that, I can't tell you if I'm going to flip heads or tails on my coin, but if I really knew everything about every air molecule and every little thing about the coin, then I could do it, right?
Right, so the idea here is that, like, maybe quantum mechanics isn't actually a complete theory, and there are things that, in a quantum description, certain information that we're missing that would be able to tell you exactly what the result of a measurement would be.
Yeah, and if you knew about all that stuff, those hidden variables, and had a theory that included them, you'd have a deterministic theory again, like something analogous to classical physics. And the weird quantum indeterministic part of quantum physics would turn out just to be an illusion. So, like, Einstein liked this idea. Later on, David Bohm liked this idea, and he had this Bohmian quantum mechanics idea, and people worked on it too. I was never exactly mainstream, but it was like, I think some smart people took it seriously. And then, Bell came along, John Bell. I think he was at CERN. And if I recall, this was in the 70s or so, I think. And he worked out mathematically that in a theory that had hidden variables, assuming it was what they call local, so no information's traveling faster than the speed of light, any theory with hidden variables that was local would have to have certain kinds of correlations between different kinds of observables you could carry out in a real-world experiment. And he wrote down this theorem. People checked it. It seemed to be right. And people then went out and did these tests. And pretty quickly, they found that there were no local hidden variables. Like that's not the answer to the question. We don't know. We still don't know if there's some sort of Copenhagen wave function collapse going on, or some sort of Everettian mini worlds thing going on. Both of those are consistent with all the data, but local hidden variable theories of quantum mechanics seem to be ruled out by these tests of Bell's theorem, or Bell's inequality, as it's sometimes called.
Right. So that it was quite significant, I guess, then, in shaping how we interpret quantum mechanics and making us go through these weird directions of multiverses and, whatever else.
The sociology of quantum mechanics in the 20th century has been pretty interesting. I guess in 21st century too. Copenhagen was pretty much the only game in town for most physicists for a long time. That was the thing you learned about in textbooks. And, no one really ever talked about other kinds, at least not very many people. Hugh Everett came along and proposed the many worlds thing, but I don't think many people took it seriously at the time. And that was in the 50s. And, Bohmian mechanics and hidden variable version of quantum mechanics, again, were out there, and Einstein liked them. So it's not like serious people weren't working on it, but it was never really mainstream. And then, I don't know, 20, 25 years ago, a lot of physicists started to take notice of this. And it's not like they wrote a lot of papers on it, because there aren't a lot of things to say about it and, that you'd put in a scientific journal. But most of the physicists I know now, or at least a lot of them, if not most of them, have opinions on this. And they're varied, and, people think different things. And, they've thought about the problem. And people have written a lot of books on it. David Deutsch and Sean Carroll wrote a book on this. And it's much more widespread pondering of this question than there ever used to be. Yeah.
Cool. So let's get to the next question.
Good.
Also from Rad. What is our best guess for how the photons that ultimately became the cosmic microwave background that we've already mentioned after recombination were generated? For example, matter, antimatter annihilation, or decay of some unknown field like inflation.
Good. So let's rewind the tape a bit, okay? So, I don't know, let's go to a point where the temperature was a tera electron volt. So this is something like 10 to the minus 12 seconds after the Big Bang, so a trillionth of a second after the Big Bang. So in this sort of circumstance, the kind of collisions that are going on between particles are kind of like the ones we study at the Large Hadron Collider. So roughly that kind of amount of energy. And, at the Large Hadron Collider, when you collide two protons together, kind of everything comes out, at least some of the time. So sometimes those collisions make photons, sometimes electrons, sometimes muons or taus or quarks or gluons or W or Z bosons or Higgs bosons, all this stuff, right? So if you put this much energy into that kind of dense, hot state in the early universe, very quickly, no matter what you start with, you will wind up with a bath of all of that stuff. Okay? So if I look at some particular particle, like an electron, in that bath, a tiny, tiny fraction of a second later, it will collide with something and become something totally different. Its energy will now be a top quark. And then that top quark, a tiny, tiny fraction of a second later, will be a W boson. And then, tiny, tiny second later, it will be a, muon and a photon and a whatever. This just constantly goes over and over and over again. So, it's hard to say that like those things were any particular kind of particle. Instead, it was just a big thermal bath of kind of everything becoming everything else over and over and over again. As the universe expanded and cooled, the temperature dropped to a point where the collisions that were taking place were lower energy and not all the particles could be created. So, for example, by the time we were a millionth of a second after the Big Bang, 10 to the minus 6 seconds, then you could still make things like, certain kinds of quarks, but not all kinds. You could make electrons and muons and photons, but you couldn't make top quarks or W bosons or Z bosons or Higgs bosons. Those were all kind of long gone. All of the ones that had existed had annihilated away and heated the bath as they did so. By bath, I just mean the bath of particles. That's what we call it. And then as things cooled even further, most of that other stuff like kind of disappeared, and we were just left with a hot bath of electrons, positrons, photons, and neutrinos. And then the neutrinos kind of stopped interacting and they just started moving in straight lines. Okay, so they're free streaming, as we call it, from that point on. And they make up the cosmic neutrino background.
Right, that would make up what we were discussing earlier, the relic neutrinos.
And around the same time, those electrons and positrons, the overwhelming majority of them annihilated away. And when they annihilated, they heated up the photons. So they made additional photons, which would all scatter with each other. And those photons, got a little bit hotter and a little bit more numerous from that process. But it's not true to say that all of the photons came from that. But all of the photons came from that series of processes that the thermal bath went through as it expanded and cooled. But then, by a little after 1 second, you pretty much were left with photons and neutrinos, and then a small abundance of things like protons and electrons thrown in for good measure.
Great. So I hope that answered your question. That was pretty comprehensive from someone who's written multiple books about this.
I'm teaching that in my cosmology class right now, so it's on the tip of my tongue.
Right. Well, thanks for asking. Okay, so we have one more question. So this is from Michael. I read that the odds of asteroid 2024 YR4 hitting the Earth based on the latest observations is now calculated to be 1 in 20,000 for its passage by Earth in 2032. But the odds of it hitting the moon was increased to 1.8%, apparently. What would happen if the asteroid hit the moon? Would it appreciably change the moon's orbit? Would that affect the Earth? If the asteroid strike caused material to be ejected from the moon, what would happen to the ejected material? Is it likely that any of it would strike the Earth or damage satellites? Do you want me to send you the link? Here, I'll send you the link.
Yeah, please do. Yeah, great. So I knew there was some asteroid that was kind of close, but I didn't, what's the mass of this thing? That's what I really need to know.
Yeah, for context, the headline does say the hazard level is at level 0, which apparently means no hazard.
Well, but they do say it's a 1 in 20,000 chance, which isn't exactly no. I mean, it's a small
That
risk.
Is some small risk.
Okay, so the thing's got a 50-meter size. All right, so let's okay. We're gonna do a physics problem in real time. All right. Let's say it's a 50-meter diameter, okay, and the volume of this thing is like 4 pi over 3 times the radius, which is 25 meters cubed. All right, so I'm getting out my calculator here. We're looking at I'm going to round to 65,000 cubic meters.
That's the volume of the asteroid.
Right. So now I want to know what the mass of the asteroid is. So volume times density. We're not being very precise here, but I don't think this is the sort of problem that requires precision. And so we are looking at something about 4 billion kilograms. Okay.
4 billion kilograms. Huh.
Okay. So what I really want to know is how much energy this thing carries from its kinetic energy. So that's 1/2 mass velocity squared. Let's just throw in 50 kilometers a second. How wrong can that be? Ooh, big number.
Hope you're happy, Michael. We're really getting you the answer. Yeah.
Fortunately, I like doing math. Okay, this is a lot. It's 1 billion tons of TNT. I think 100 megatons is roughly as big as any nuclear weapon. This is 10 times bigger than that.
Okay. Okay, so that sounds big. I mean, okay, I will say in this article, they do say that it's not an Earth destroyer size.
Yeah, okay. That's consistent with this. I mean...
Yeah, but it could destroy a local area. But the question was about whether it could shift the moon's orbit.
Yeah. Let's compare it. So I think what's relevant is what is the kinetic energy of this thing compared to the kinetic energy of the moon? That might be give us some idea. Okay. So the mass of the moon, you can hear me Googling, is about 10 to the 23 kilograms. But now bear in mind, this thing was only 4 times 10 to the 9. So this thing is way, 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 way smaller than the moon. So I suspect that means the moon's orbit is going to be fine. It'd be a hell of an explosion, though. Wow.
Yeah.
Part of me wants it to happen.
Do you think we could see it?
Yeah. Yeah, of course.
Yeah. You could see it.
Well, maybe it'd have to hit a side of the moon you could see.
The side of the moon we could see.
I don't know. But maybe either way. I mean, it's a big explosion.
You could see it, but it probably wouldn't shift the moon's orbit or, cause the moon to start hurling towards Earth or anything like that.
No. I mean, of course, anything will shift the orbit a little bit, but I don't think this is enough to.
But
shift
it could be, a millimeter.
Yeah, I don't know how to do that estimate right now, but it would be small. It'd be small.
Yeah.
Yeah.
So it seems like we don't have to worry about that. Maybe we'd have to be concerned if it was heading towards the Earth.
Yeah, I mean, if it hit Earth, so the problem is it would send a bunch of dust up into the atmosphere and, block sunlight for some period of time. That's probably besides the region that it hits. But for the rest of the Earth, it would, people talked about nuclear winter in this way. If we had a large-scale nuclear exchange, the amount of debris in the atmosphere might actually be worse than the nuclear exchange itself, in the long run.
Wow. Well, I guess you said this was about larger than, was it 10?
Yeah, this would be 10 times bigger than the biggest nuclear weapons that have ever been built.
Okay, so if there was a nuclear war where there were 10 nuclear bombs dropped, that would be
the 10 of the biggest. Most of them are smaller, right? Most of our weapons.
10
are
of the
smaller.
largest nuclear weapons.
Right.
That would be about as bad as this asteroid hitting us.
If this thing hit Earth, I'm not saying it would be Earth ending, but it'd be real bad.
Destructive, yeah.
Yeah.
Well, good thing that we don't have to worry too much about that, it looks like.
Yeah, 1 in 20,000. Sleep well at night.
Okay, great. Well, that was all of our questions.
That was fun.
Thank you all so much.